Hey guys, we're going to now solve some linear equations using the elimination method. But before we get started, we're going to go over some review. So if you don't need this review, be sure to fast forward this video to the time that is timestamped in the caption below the video, okay? For those of you who are watching, we are first going to go over the forms of linear equations. First, we have point-slope form. Hopefully we all know point-slope form in your head, and you should always be trying to do these things in your head before I write them down. Point-slope form of a line requires us to have a point and a slope. It's the favorite equation of mine, and that one would be y minus y sub 1 equals m times the quantity of x minus x sub 1, where the point being mentioned is in the equation as x sub 1 comma y sub 1. The x and the y without the subscripts really just stay in the equation as they are, and the slope is described by the letter m. We really like this form. Something I'm going to throw in here is that we can, I already started writing y sub 1, we could also think of this as y minus k equals a times x minus h. In Algebra 2, when you graph, you use something called transformations, where h and k represent our graph moving left and right, and k, this part, would represent your graph moving up or down, and then a is described as a vertical stretch or a vertical compression, and really linear equations can be thought of in this way, and you may even get yourself eventually to a place, and this is just some foreshadowing, where you might look at it a little bit more like this, where the y is isolated, and you may have a square out here, and this won't be a line, it'll be a parabola, it'll be a quadratic equation, you'll have a square root equation, absolute value for an absolute value equation, and so on, and this transformation will really work for everything. Next, slope-intercept form. Slope-intercept form is a little bit more middle school if you ask me, but I know some people really like it. I don't love it because B restricts you to using the y-intercept, and sometimes it's just way more convenient to use really any other point than the y-intercept, but it's all good. If you have m equal to 0, then you have y equals 0x plus b, which is really y equals b, which is just y equals some number, which is actually the equation of a horizontal line, which we will talk about later. Next, standard form. Standard form can vary from book to book. Sorry, that's an A. I randomly wrote it differently. AX plus BY equals C. We use capital A, B, and C. This B value has absolutely nothing to do with this B value. Okay? Please don't think they're the same. They have nothing in common. Rules. We have a few rules that we like to instill for this. Our rules are that A, B, and C are all integers. If you don't know what an integer is, please look it up. It should be in your notes somewhere. You should know it. And if you don't, and if this is really quite new for you, looking it up is still the best way to remember, because if I tell you right now, you're not going to remember, okay? So please go check it out. A, B, and C are all integers, but an extra part of this rule is A is greater than 0. In other words, I don't know why I'm randomly capitalizing, so let's do that. In other words, A is positive. This is just sort of to ensure that we all write our equations the same way. It really is just for convenience. So when we compare answers to one another, we can quickly and easily decide whether or not we're doing the same thing. Up next, we are going to just go over a little bit with parallel and perpendicular lines. Parallel lines, that's the symbol for parallel lines. Parallel lines is going to be a huge concept in geometry. When we are really talking about parallel lines in the coordinate plane, in the XY plane or Cartesian coordinate plane, you are going to be really talking about them as equations. We kind of refer to that often as coordinate geometry. So you do want to tie it to as much algebra as possible so we can make connections for longer throughout your math experience. So there's the symbol for parallel lines. Something that's really good to know. Parallel lines, I'm just going to make a quick statement, have the same slope. Parallel lines have the same slope. Now, if you are given an equation in, say, standard form, ax plus by equals c, that is not equal to the slope. A lot of people think if it's in front of a, it's the slope, okay? Not equal. How do you get the slope here? Well, you subtract ax, if you really think about this, right? So by equals negative ax, or really opposite of ax, because if it were negative, now it's positive, yada, yada, plus c. Then we divide by b. So y equals negative a over b, x plus c over b. So, in conclusion, if we're given a line in standard form, it's safe to say the opposite of a over b is equivalent to the slope. So you don't have to do so much work. Good to know, okay? Parallel lines, there's the symbol. Parallel lines have the same slope. A in front of the x is not equal to m, okay? A out front of the x, I know it's in front of the x, but guess what? It doesn't mean it's the slope. It is not equal to m. If I wanted to find the slope, sure, you could take a while and change it into slope-intercept form. Subtract ax and divide by b. But let's just do it one time over here, conceptually, and kind of gain some knowledge on it. If I wanted to get y by itself, so it looks like y equals mx plus b, it looks like slope-intercept form, which we did up there, right? You're going to subtract ax, or really do the opposite operation. So we brought ax to the other side, then we're going to divide by b. In conclusion, we can say a over b, opposite of a over b, is equal to m, or the opposite of a over b is equal to the slope. Now, for perpendicular lines, the symbol looks like this, and we can say that perpendicular lines have opposite and negative in math really mean the same thing. If something's positive, it becomes negative. Negative becomes positive. Opposite, reciprocal. Now, I know we use these words together a lot right now, but opposite, reciprocal, those are two different words being applied here. This changes the sign. This makes it 1 over the number, or really as a shortcut, I guess you could say it flips over your fraction. Have opposite reciprocal slopes. So, example, 2/3 would become negative 3 over 2. These two are perpendicular. They also intersect at 90-degree angles. They don't just intersect, they intersect at right angles. So this is all really good to know. Last, we have a few things about horizontal and vertical lines to go over. So what can we say over here? A trick I have, I always use the phrase, hey, vex over the years. What does it mean? Really nothing. But horizontal equations are y equals something, and vertical equations are x equals something. Now, that's just a little trick for people who have a little bit of trouble maybe understanding the concept. But really, if you have a horizontal line, it goes the way of the horizon, okay? Right? Horizon. So a horizontal line goes that way. What does every point on a horizontal line have in common? They all share the same y value. So that's why the equation of the line is y equals a number. So this is the equation of the line. A vertical line goes the other way, up and down, okay, north to south, I guess, if you're thinking of it as being drawn on a map. And those equations, all right, those equations are going to be x equals a number, because what do they all have in common? They all have the same x value. 1, 1, 1, 2, 1, 3, 1, 4, something like that. Horizontal equations, y equals a number. Vertical equations, x equals a number. Now that's just the equation of the line. What about the slope of the line and the slope of this line? Well, those are important, and people mix them up and fuse together equations and slopes and all that. So the slope of a horizontal line is 0. It is all run, so 0 rise, 1 run. Okay? When we set a 0 on top, that's okay. It equals 0. Okay? Here, the slope of a vertical line, that's a U, and U is for undefined. A vertical line is all rise and no run. 0 in the denominator, well, that's a big no, okay? Undefined. You could even write UND. Problem area over here, a little troublesome, okay? So that's some quick stuff about horizontal and vertical lines. Here we have a quick example that we are going to do with graphing first, and then we are going to go ahead and also solve it using elimination. In the last lesson, we focused on substitution. These are all Algebra 1 strategies, techniques, things that you should have learned in Algebra 1 that will become relevant in Algebra 2. Well, Algebra 2, yes, and in geometry. So here is my first equation. This equation is given in standard form. When lines are given in standard form, do not waste time. Okay, we want to be efficient, and we're going to go ahead and graph this using the trick we did in the last video. So in the last video, we went ahead and graphed this by finding intercepts. If I want to find my y-intercept, I plug in 0 for x. Negative 3y is 6. Y equals negative 2. Here's my y-axis, slow and steady, so you plot it in the right place. Don't get distracted. So there we go. My y-intercept is negative 2. Now, I'll label that in a second, but I like to plot the other point first so I know where I have space. If I want to plug in 0 for y, I get my x-intercept, and I'll see that x equals 3 from that. So I just solve 2x equals 6, and I get 3. Okay? So if the line's going to be going this way, I'll probably label my points over here. And there we go. So I plotted 0, negative 2, and I have 3, 0, connected those 2 points because 2 points determine a line, and we have our equation graphed, all good and done. It's also pretty quick and easy to see that my slope is up 2 over 3, and we just said it's the opposite of A, negative 2 over B, negative 3, negative 2 over negative 3, it's positive 2 over positive 3. So 2/3 is my slope. Now we're going to do this line over here, again by finding intercepts. So if I want to find my y-intercept, y-axis, I plug in 0 for x, 6y equals 15. Divide by 6, so I'm going to get y equals 15 over 6. They both reduce by 3, which gives me 5 over 2, or 2.5, and it's positive. Don't cover up that sign. Be careful because that'll affect your answer. So y-intercept of 2.5. And my x-intercept, I'm going to plug in 0 for y. 3x equals 15, so x equals 5. Now I'm going to go ahead and graph that and label. Now there we go. We have our 2 lines graphed, and as you can see, it's more often than not you're going to be in a situation where your point of intersection is not perfect. Maybe in Algebra 1, maybe sometime in middle school when you first were introduced to such a concept, you were always given pretty nice examples just to ensure that you were doing things correctly. So this is right there. That's our solution. And now what we're going to do is we're going to use algebra, specifically the elimination method, to solve this system of equations and get the exact coordinate point where they intersect. And we should have some pretty good number sense so we know if it makes sense or not. First thing I'm going to do is write down my 2 equations. If you like to color coordinate, then you can do just that. 2x minus 3y is equal to 6. And my next one was 3x plus 6y. 3x plus 6y is 15. Now, when you're doing the elimination method, what you want to do is, I like it when my equations are both in standard form, or at least almost perfect standard form if possible. And I try to make sure that my variables, my x terms are above each other, my y terms are above each other, my plus or minus signs, my equal signs, and my constant term. They are all stacked up neatly. Now, what I want to do is I want to make sure my coefficient in front of my x and my y, or really not and, the coefficient in front of my x or the coefficient in front of my y are either the same number or opposite numbers. I would also rather try to make sure that I make numbers smaller before I go ahead and make them bigger, because when you make them bigger, you often make things more complicated than they need to be. So I could double everything here. If I double everything, 4, 6, and 12, or I could divide by 3, 1, 2, and 5, divide by 3, and then multiply by 2. 1, 3, 2, and 5 if I divide by 3, but multiply by 2, and then this will be a 2x, this will be a 4y, and this will be a 10. So really, it doesn't matter which way you do, or I can multiply by 2 and multiply by 3 and make these both 6, okay? I guess I'll do it the most interesting way. So I will leave my first equation as is. So I'm just going to draw an arrow. 2x minus 3y is equal to 6. Now for this one, if I divide by 3 first, like I said, I'll get x plus 2y is 5. And then I'm going to multiply by, I don't remember what I said I wanted to multiply by. I guess I can multiply by 2. So then I get a 2x in front of there. So if I multiply by 2, I get 2x plus 4y is 10. There we go. Now some of you might be all up in arms upset because you're like, I thought this had to be negative. Sure, it does have to be, I guess, negative. But the way I like to think of it is when they're the same sign, the numbers that have the same absolute value in front of them, really, 2 and 2. Instead of adding my equations together when they're negative, you really add them together, okay? Important concept. I'm going to subtract my entire bottom equation. See these beautiful parentheses I'm adding on here? I subtract this entire equation from that entire equation. I don't write my distributed negative in here because most of the time you're writing in pencil and you can't remember what was there and what wasn't. What's 2x minus 2x? That's right, it eliminated, 0x. What's negative 3y minus 4y? Good, negative 7y. What is 6 minus 10? Negative 4. Just take your time and you're good to go. Divide by the negative 7 and y equals 4/7. That is just the y coordinate of my solution. So I'm going to put in that 4/7. It's around a half, that y value. If you look over here, it seems appropriate. It's good number sense. Now, when you solve by elimination, a common misconception is that you have to go back and find your x value using elimination also. That's just not the case. Now, you could just take this right over here, fill it into either equation, really, and solve for your x value. Now, I'm going to go ahead and solve for this right here because I already cleaned it up and made it a little smaller. So I'll have x equals, if I bring 2y over, I have 5 minus 2y. I just did that, so I'm a little bit ahead. Now, I'm going to fill this in for y. X equals 5 minus 2 times 4/7. You do not need a common denominator for multiplication. X equals 5 minus 8 over 7. 5 is really over 1, but that's really 35 over 7 minus 8 over 7. So that's going to be equal to 27 over 7. And that's a little bit less than 4 because 28 over 7 is exactly 4. So 27 over 7. And that right here is your solution, your answer, your main goal of this problem. If you look over here, it does look about right. It's about 4 over and about a half up, and that's approximately what those are. equal to. So in conclusion, when you solve by elimination, if they're both positive or both negative, keep in mind, they're the same sign. In order to eliminate, you have to incorporate some opposite operation. I like to leave the parentheses there, parentheses, minus sign, underline, cancel. You'll hear me say that a million times. Parentheses, minus sign, underline, cancel. Then I solve from there, okay? If they're already opposites, sure, you could add them straight down. If they're already opposites, you add them together and it eliminates. So think carefully before you do a problem like this and make sure you graph first in the meantime to make sure that you're at least aware if your numbers, your ordered pairs make sense or not. Good luck.